Okay, this video is about derivatives of some standard function. So I have a bunch of functions on this side, and I'll denote their derivatives on this side. So this column represents my functions. I'll represent it with either a y or an f of x, and correspondingly the derivative will be either dy by dx or f prime of x, f dash of x, or as we say. So the very first function that I want to look at is this very simple looking power function. It is nothing but your variable x raised to the power n, and this n can be any number. It can be positive, negative, integer, rational, irrational. It can be anything. So if you have a function like this, its derivative with respect to this variable x is nothing but this expression, this function. So this function, what you do is you take the power n and you multiply it with your expression, and then you reduce the power with 1. So I have taken this power n outside, so it becomes n times, and then this is nothing but x raised to that same power, but 1 less than that. It's just x raised to uh, n minus 1. So you'll see using just this rule, or using just this derivative, you can find derivatives of a lot of other functions. And then okay, let me tell you that this is not God given. There is a proof for this, and maybe we'll do that in future videos. So you just don't take this for granted. There is a proof for this. It's just out of the scope of this video. So we'll see that using this derivative, we can find derivatives of other functions. For example, a constant. Now I know derivative of a constant is 0, but you can say that a constant is actually, I'll do it over here. A constant, isn't it just that k multiplied by x raised to 0, right? And taking the derivative of this is as good as taking the derivative of this, which is nothing but k times a function. Now, we'll learn in future videos that if you have a multiple of a function, you can take that multiple outside and just worry about its that function's derivative. So I can worry about if I want to find the derivative of this, it's as good as taking the k outside and then talking about the derivative of what is inside. So what is inside is a power function. It's x raised to 0. So what I do is, according to this, it is nothing but 0 times x raised to 0 minus 1 is minus 1. And then we know anything multiplied by 0 is 0. So this gives you 0, and then whatever k may be, this whole product gives you a 0. So this is not new. This actually can be derived from the this power rule derivative only. So this actually is 0. Derivative of a constant is 0. You can consider that as a rule, or you can prove it from this basic definition. The other basic derivative is that of a linear function, just x. So x is nothing but x raised to 1, right? And so according to this rule, it is nothing. The derivative is, if this is a y, then dy by dx is nothing but, what you take is you take this derivative outside. You take this power outside. I'm sorry. So 1 comes outside, and then I reduce my power by 1. So it's already x raised to 1. This now becomes x raised to 1 minus 1. 1 minus 1 is nothing but 0. And we know that anything raised to 0, non-zero, is 0, is actually 1. So this is actually just 1 times 1, which is just 1. So yeah, the derivative of a linear function x is just 1. You can either take it as is, or you can also derive it from this technique. The other important derivative is that of square root x. Now square root x is can be written as x raised to 1/2, because that's what square root means. It's as good as taking the 1/2 power. So if I say this is my y, then dy by dx will be, again, use the same rule. You take the power outside, so you take this half outside, and then you reduce the power by 1. The power is already half, so if I reduce it by half, reduce it by 1, it becomes a negative half, right? And then we know that what negative power of negative half means. It actually means this half as is. This actually means 1 by x to the half power, right? Because a negative exponent is as good as 1 by that expression raised to the positive exponent. And something raised to half is nothing but it's a square root. So I can replace this with square root x. So what we are left with is nothing but this is just 1, the numerator is just 1, divided by, there's a 2 in the denominator along with a square root x, I'm sorry. So this is nothing but 1 by 2 root x. So if I were to write it over here, the derivative would be 1 by 2 times square root x. And yeah, the next function is 1 by x, and also we know that 1 by x is nothing but x raised to minus 1. So if I were to take this as my y, my dy by dx would be again with the same rule. You take the power outside, so I take this power minus 1 outside, and then I reduce my power by 1. So this becomes x raised to minus 2, and x raised to minus 2 is nothing but 1 by x squared. So this can be written as negative 1 by x squared. So yeah, that's what the derivative is. The derivative of 1 by x is minus 1 by x squared. So using just one technique, we have found the derivative of a bunch of standard functions. The other important technique is that of this exponentiation. So if you have a constant being raised to your variable, now this is different. This is different than this, because here your variable was being raised to an exponent. Here you have some base being raised to your variable. So you have a base a which is being raised to power x. Its derivative is this express this function. Again, there's a proof for that. We'll maybe do that in future videos, but let's for now take it for granted. Its derivative is nothing but that same expression a raised to x multiplied by the log of a. And when I write log of a, it means the natural log of a. It means the log to the base e. Some people write it as ln of a to denote natural logarithm of a, but I'll write it as just a. So this is the derivative of the function a raised to x, and now using this definition or using this technique, we can find the derivative of other functions such as e raised to x. So according to this technique, if my y is just e raised to x, so its derivative will be that same expression e raised to x multiplied by log of e. Now since my log of e is to the base e is just 1, I can get rid of that. So this is just e raised to x. So yeah, you get the very famous derivative that the function e raised to x has itself as its derivative, and it also comes from this technique, this general technique. And the other standard derivative is that of log x. This the derivative of log x is just this function 1 by x. So yeah, I'll leave it over there, and these are just some standard function, the derivatives of some standard functions.